Deep beneath the border of Switzerland and France, physicists built a machine that stretches 27 kilometers in a circle. They use it to smash particles together at 99.9999% the speed of light. They have recreated conditions that existed 1/trillionth of a second after the Big Bang. They have manufactured antimatter, trapped it, weighed it, and dropped it. And after decades of searching for a flaw in the fundamental laws of physics, they found something nobody expected. Not a crack, not a failure, a rule so deep and so rigid that reality itself appears unable to violate it. Every test confirms it, every experiment reinforces it, and it might explain why the universe exists at all. If you enjoy journeys that change how you see reality, hit that like button and subscribe. Now, settle in and get yourself comfortable. Let's begin. There is a place on Earth where humans routinely create the most extreme conditions in the known universe. Not inside a volcano, not at the core of a nuclear reactor, not even at the detonation point of a thermonuclear weapon. The most extreme temperatures, the most violent collisions, the highest concentrations of energy anywhere on this planet occur in a circular tunnel buried 100 meters beneath farmland on the border between Switzerland and France. The tunnel runs underneath villages where people walk dogs and buy groceries. It passes beneath wheat fields where tractors still follow the same routes they have followed for generations. And inside that tunnel, 27 kilometers in circumference, two beams of subatomic particles race in opposite directions at 99.999991% the speed of light. The European Organization for Nuclear Research, known worldwide by its French acronym CERN, operates this machine. It is called the Large Hadron Collider, and it is the single most complex piece of engineering humanity has ever built. Not one of the most complex. The most complex. More than 1,200 superconducting dipole magnets, each one cooled to -271.3 degrees Celsius, colder than the vacuum of deep space, bend the particle beams around the ring. Another 392 quadrupole magnets focus the beams into threads thinner than a human hair. Radio frequency cavities accelerate the particles with each lap, pushing them closer and closer to the speed of light. When the beams reach full energy, each proton carries 13.6 trillion electron volts of kinetic energy. That is a quantity so enormous that a beam containing 300 trillion protons carries enough total energy to melt a 500 kilogram block of copper on impact. These beams do not simply travel in circles. They are made to cross. At 4 specific points around the ring, the two counter-rotating beams are steered into head-on collision. When protons traveling at nearly the speed of light smash into each other, the energy of their collision is concentrated into a region smaller than an atomic nucleus. Temperatures at the collision point briefly exceed 5.5 trillion degrees Celsius, more than 100,000 times hotter than the core of the Sun. These conditions have not existed naturally in the universe since the first trillionth of a second after the Big Bang, and they do not happen once in a while. They happen 600 million times every second, 40 million beam crossings per second, each one producing an average of roughly 50 individual proton-proton collisions. The purpose of all this violence is not destruction, it is archaeology. The collisions at CERN are designed to recreate the conditions of the newborn universe. By concentrating extreme energy into infinitesimal volumes of space, physicists force matter to behave the way it did when the cosmos was less than a heartbeat old. Particles emerge from these collisions that have not existed freely since the universe began. Forces reveal themselves that are normally buried beneath the calm surface of everyday matter. The Large Hadron Collider is not a bomb. It is a window into the past, a telescope aimed not at distant galaxies but at the first instant of time. CERN itself is older than most people realize. It was founded in 1954, just 9 years after the end of the Second World War. 12 European nations signed its founding charter, with a mission that was as much political as scientific. The idea was to unite European countries through peaceful scientific collaboration in the aftermath of a catastrophic war. The original acronym stood for Conseil européen pour la recherche nucléaire, the European Council for Nuclear Research, though the name persists even though the organisation long ago outgrew its original scope. Today, CERN has 24 member states. It employs roughly 2,500 staff directly, and it hosts more than 12,000 visiting scientists from over 110 countries. Physicists from nations that are geopolitical rivals work side by side in the same experimental halls. The laboratory operates in English and French. The cafeteria serves food from a dozen culinary traditions. And the shared language, the one that transcends all borders, is mathematics. The track record of discovery that has emerged from this international collaboration is staggering. In 1973, physicists using a device called the Gargamel bubble chamber detected weak neutral currents for the first time, confirming a crucial prediction of the electroweak theory that unifies electromagnetism with the weak nuclear force. A decade later, in 1983, CERN announced the discovery of the W and Z bosons, the massive particles that carry the weak force. That discovery earned Carlo Rubbia and Simon van der Meer the Nobel Prize in Physics the following year. In 1989, a British computer scientist named Tim Berners-Lee, working at CERN to improve information sharing between research groups, invented the World Wide Web, the technology that transformed human civilization, that reshaped commerce and communication and culture across the entire planet, was born as a side project at a particle physics laboratory. CERN made the software freely available in 1993, asking for nothing in return. Every website you have ever visited traces its ancestry to that decision. But the crowning achievement came on the 4th of July, 2012. On that day, the ATILAS and CMS experiments at the LHC announced the discovery of a new particle consistent with the Higgs boson. The Higgs had been predicted in 1964 by a group of theorists, including Peter Higgs and François Englert. It was the final missing piece of the standard model of particle physics, the particle responsible for giving mass to all other fundamental particles through its interaction with a field that permeates all of space. Finding it required building the most powerful accelerator in history and constructing detectors capable of picking out the Higgs signal from trillions of background events. The discovery confirmed that the theoretical framework physicists had been constructing for half a century was correct. Higgs and Englert received the Nobel Prize in Physics the following year. And in 2025, the four main LHC experimental collaborations, ALICE, ATLAS, CMS, and LHCb, were collectively honoured with the Breakthrough Prize in Fundamental Physics for the body of work produced during the LHC's second operating period. This is the institution that now turns its attention to the deepest symmetry in physics, not a scrappy upstart laboratory making bold claims. The most successful experimental physics facility in human history, with a 70-year record of discoveries that have reshaped our understanding of the universe at its most fundamental level. When CERN produces a result, the physics community listens. And what CERN has been finding in its antimatter experiments deserves close attention. The Large Hadron Collider dominates the public image of CERN, but the laboratory is far more than a single machine. The LHC sits at the top of an accelerator chain, a sequence of progressively more powerful devices that boost particles to higher and higher energies before injecting them into the main ring. Protons begin their journey in a simple bottle of hydrogen gas. The atoms are given an extra electron, turning them into negatively charged hydrogen ions. And these ions enter LINAC 4, a linear accelerator that boosts them to an energy of 160 million electron volts. At injection into the next machine, the proton synchrotron booster, the electrons are stripped away, leaving bare protons. From there they pass into the proton synchrotron booster, then into the proton synchrotron, then into the super proton synchrotron, each ring larger and more powerful than the last. Only after passing through this entire chain do protons finally enter the LHC, where they are accelerated to their full collision energy. The whole process takes about 4 minutes. Surrounding the 4 collision points are detectors the size of apartment buildings. Atlas, the largest, measures 46 meters long, 25 meters in diameter, and weighs approximately 7,000 tons. CMS, its counterpart on the opposite side of the ring, is denser and heavier at 14,000 tons, despite being slightly smaller. These are not simple cameras pointed at the collisions. They are onion-layered instruments with dozens of sub-detector systems, each one designed to capture a different type of particle or measure a different property. Innermost tracking layers record the curved paths of charged particles as they spiral through magnetic fields. Calorimeters absorb particles completely, measuring their total energy. Muon chambers at the outermost layers catch the muons that penetrate through everything else. A single collision event generates roughly 1 megabyte of compressed data. With 600 million collisions per second, the raw data rate exceeds 1 petabyte per second. No storage system on Earth can handle this, so sophisticated trigger algorithms running on custom electronics make split-second decisions about which events are interesting enough to save. Only about 1,000 events per second survive this filtering, and even that reduced stream fills data centers across the globe. 2 other major LHC experiments complete the picture. LHCb, the B standing for beauty, specializes in studying particles containing bottom quarks, also known as beauty quarks. These particles are short-lived, but their decay patterns encode information about the subtle differences between matter and antimatter. ALICE, a large ion collider experiment, studies what happens when the LHC collides. Not protons, but heavy ions, typically lead nuclei containing 208 protons and neutrons. These heavy ion collisions create a state of matter called quark-gluon plasma, a hot, dense soup, where quarks and gluons are no longer confined inside individual protons and neutrons, but move freely across a larger volume. This state of matter last existed naturally in the universe, approximately 1/millionth of a second after the Big Bang. In 2025, the LHC collided oxygen and neon ions for the first time in its history, opening entirely new avenues for studying nuclear matter under extreme conditions. But the Large Hadron Collider and its massive detectors are not the only tools at CERN probing the foundations of reality. On the opposite end of the energy spectrum from the LHC's brute force collisions sits a quieter, more delicate program. The antiproton decelerator is a machine that does exactly what its name suggests. It takes antiprotons, the antimatter counterparts of ordinary protons, and slows them down. While the LHC accelerates particles to the highest achievable energies, the antiproton decelerator does the opposite. It takes antiprotons produced by slamming a high-energy proton beam into a metal target and reduces their speed by a factor of roughly 1 billion. The slowed antiprotons are then passed to an even gentler machine called ALINA, the extra low-energy antiproton ring, which decelerates them further still. These slow, cold antiprotons are delivered to a collection of experiments with names like ALPHA, BASE, AEGIS, and G-bar. Each of these experiments traps antiparticles in magnetic or electromagnetic cages and measures their properties with exquisite precision. Some of them go a step further. They combine antiprotons with positrons, the antimatter counterpart of electrons, to create antihydrogen, an atom made entirely of antimatter, according to everything physicists understand about the universe, should have exactly the same properties as an ordinary hydrogen atom, except with every charge reversed. Antihydrogen does not exist naturally on Earth. It barely exists in the natural universe at all. These experiments manufacture it, trap it, hold it for minutes or even hours, and then measure it. And the question they are asking is one of the most fundamental in all of science. Is antimatter truly the perfect mirror image of matter, or is there a flaw in the reflection? The reason this question matters reaches far beyond academic curiosity. It touches the most disturbing unsolved problem in physics, a problem so fundamental that it concerns the existence of everything around you. Every atom in your body, every star in the sky, Every grain of dust on the surface of Mars, none of it should be here. The Big Bang, according to every equation physicists have ever written and tested and confirmed, should have produced exactly equal amounts of matter and antimatter. This is not a guess. It is a prediction that follows directly from the symmetry properties of the fundamental forces. When energy converts into mass, it always creates a particle and an antiparticle together. A photon of sufficient energy can produce an electron and a positron as a pair. A gluon interaction can produce a quark and an antiquark as a pair. The early universe was an ocean of energy, unimaginably dense, unimaginably hot. As it cooled, that energy crystallized into matter. Particles and antiparticles condensed out of the primordial fireball in perfectly matched pairs. For every proton, an antiproton. For every electron, a positron. For every neutrino, an antineutrino. Perfect symmetry, perfect balance. And then something should have happened that would have prevented you from ever reading these words. Matter and antimatter annihilate each other on contact. When a particle meets its corresponding antiparticle, both are destroyed. Their entire mass converts into energy, typically in the form of high-energy photons. The process is perfectly efficient. Nothing is left over, nothing remains. If the Big Bang produced equal quantities of matter and antimatter, every particle should have found its opposite number and annihilated. Picture what this annihilation would have looked like had you somehow been there to witness it. In the first seconds after the Big Bang, the universe was a blinding maelstrom of energy and matter, denser than anything that exists today. Temperatures exceeded trillions of degrees. Particles and antiparticles were being created and destroyed in a continuous frenzy, popping into existence from pure energy and vanishing back into radiation, in a cycle that repeated trillions upon trillions of times every second in every cubic centimeter of space. As the universe expanded and cooled, the energy available to create new particle-antiparticle pairs diminished. Creation slowed, but annihilation did not slow with it. Particles continued finding their antiparticles and destroying each other. The cosmic population of matter and antimatter plummeted. The universe was cannibalizing itself. If the symmetry between matter and antimatter were truly perfect, this annihilation would have been total. Every last proton would have found an antiproton. Every electron would have met a positron. The final act of creation would have been the final act of destruction. The universe would have become a thin, cooling bath of photons expanding forever into darkness. No atoms would have formed. No stars would have ignited. No galaxies would have assembled. No planets would have coalesced from swirling disks of rock and ice. No water would have pooled on any surface. No chemistry would have begun. No molecule would have replicated. No cell would have divided. The cosmos would be a vast, featureless void filled with nothing but light, growing colder and dimmer for all eternity. Not empty in the way that intergalactic space is empty, where atoms are simply rare. Empty in the most absolute sense, devoid of structure, devoid of matter, devoid of possibility. A universe where nothing can ever happen because there is nothing left for anything to happen to. And yet here we sit, on a planet made of matter, orbiting a star made of matter, in a galaxy made of matter, in a universe that is, as far as every observation can determine, overwhelmingly, crushingly, almost exclusively made of matter. For every particle of antimatter detected in cosmic rays, there are approximately 10 billion particles of ordinary matter. Antimatter is not just rare, it is virtually absent. The universe picked a side, and it picked matter. The question that has consumed physicists for decades is simple to ask and ferociously difficult to answer. Why? Something broke the symmetry. In the first fractions of a second after the Big Bang, some process tipped the balance in favor of matter over antimatter. The imbalance was not large. It was, by any reasonable measure, minuscule. For every 10 billion antimatter particles produced, there were 10 billion and 1 matter particles, one extra particle in 10 billion. That was the surplus. And when the great annihilation was over, when every particle that could find an antiparticle had found one, and both were destroyed, that tiny surplus was all that survived. One particle in 10 billion. Everything in the observable universe, every galaxy, every human being, every atom of every element on the periodic table, traces its ancestry to that almost imperceptible excess. You exist because the universe was not quite symmetric. You are a rounding error in the cosmic ledger, and so is everything you have ever seen or touched or loved. This is called the matter-antimatter asymmetry problem, or sometimes the baryogenesis problem, and it's been one of the central open questions in physics for more than half a century. The standard model of particle physics, the theoretical framework that describes all known fundamental particles and 3 of the 4 fundamental forces, can account for some asymmetry between matter and antimatter. A phenomenon called CP violation, discovered at Brookhaven National Laboratory in 1964 and studied extensively at CERN ever since, shows that certain processes in nature treat matter and antimatter slightly differently. The weak nuclear force, one of the 4 fundamental forces, does not interact with particles and antiparticles in a perfectly symmetric way. This provides a mechanism through which an imbalance could develop. But there is a problem. The amount of CP violation that the standard model predicts is not nearly enough. Not by a small margin, by many orders of magnitude. The standard model's contribution to the matter-antimatter asymmetry falls short of the observed value by a factor of roughly 1 billion. This is not a small discrepancy. This is a chasm. Something beyond the standard model, some unknown particle or unknown force or unknown process, must have contributed to the asymmetry. And finding that something has been one of the driving goals of particle physics for decades. CERN has been attacking this mystery from every available direction. The LHC searches for new particles that could introduce additional sources of CP violation. LHCb measures the known CP violation with ever-increasing precision, searching for deviations from standard model predictions that might hint at new physics. The CMS collaboration has recently demonstrated that machine learning can outperform traditional methods in the full reconstruction of particle collisions, opening new avenues for extracting subtle signals from the vast oceans of LHC data. The antimatter experiments at the antiproton decelerator measure the properties of antiparticles and antiatoms to extraordinary accuracy, looking for any difference between matter and antimatter that current theories do not predict. And in all of this searching, across decades of experiments and trillions of recorded collisions and measurements pushed to the furthest limits of human technology, physicists keep running into the same invisible wall. Not a wall that blocks discovery, a wall that defines the boundary of what is possible, a constraint so deep and so absolute that no measurement has ever found a way around it, over it or through it. No matter how hard they look, no matter how precisely they measure, no matter what system they study, the same rule holds. Every time, without exception. That rule is called CPT symmetry. The letters stand for 3 mathematical operations. C stands for charge conjugation, which means replacing every particle with its antiparticle. P stands for parity, which means reflecting everything in a mirror, swapping left and right. T stands for time reversal, which means running the entire process backward, reversing every motion and every sequence. CPT symmetry states that if you perform all 3 operations simultaneously, if you replace all particles with antiparticles, flip left and right, and reverse the direction of time, the resulting physical process is indistinguishable from the original. Not approximately indistinguishable, not close enough for practical purposes. Perfectly, exactly, mathematically indistinguishable. Each of the 3 individual symmetries can be broken. Nature has proven this. Parity, the mirror symmetry, was the first to fall. Charge conjugation fell with it. Then CP, the combined operation of charge and parity, was shown to be violated as well. Even time reversal symmetry, the last to be tested directly, turned out to be broken. The details of how each one cracked are extraordinary stories in their own right. Each piece of the triad, taken alone, cracks under experimental pressure. Every individual symmetry in the CPT combination has been shown to fail in at least one physical system. But when all three transformations are applied simultaneously, the cracks vanish. The broken pieces reassemble into something whole. CPT symmetry has been tested in laboratories around the world, across different particle systems, at different energy scales, using different experimental techniques. No experiment has ever detected a violation. Not once, not at any precision level, not in any system. What makes this particularly striking is that CPT symmetry is not merely an observed pattern, it is a mathematical theorem. In 1954, the physicist Gerhard Luders proved, building on work by Julian Schwinger and Wolfgang Pauli, that CPT symmetry is a necessary consequence of the basic mathematical structure of quantum field theory. Any theory that respects the principles of special relativity and quantum mechanics, any theory in which physical effects propagate locally through space, rather than jumping instantaneously from one location to another, any theory with a stable lowest energy state must automatically respect CPT symmetry. It is not optional. It is not a feature that theorists can choose to include or exclude. It is baked into the mathematical bedrock of the framework that describes everything we know about the fundamental behavior of matter. This means that violating CPT would not be like discovering a new particle or a new force. It would be like discovering that quantum mechanics is wrong, or that special relativity is wrong, or that both are wrong. It would require abandoning not just a specific theory, but the entire framework within which all successful theories of particle physics have been constructed. The standard model would collapse. Quantum electrodynamics, the most precisely tested theory in the history of science, would collapse. Everything built on quantum field theory over the past 80 years would need to be rebuilt from the ground up. The stakes, in other words, are total. CPT symmetry is not just another law of physics. It is the law that guarantees the internal consistency of every other law. It is the hidden rule that ties the structure of space-time to the behavior of particles and forces. It is the deepest symmetry ever identified in nature. And CERN has built the most sensitive experiments in human history to test whether it truly holds. The results of those experiments carry implications that ripple outward through every branch of physics. They constrain theories of quantum gravity. They eliminate entire families of speculative models. They place boundaries on what new physics can look like. They tell us that whatever unknown process tipped the balance between matter and antimatter in the early universe, it did so while respecting CPT symmetry. It found a way to break the mirror without breaking the frame. Understanding how CERN tested this rule, what the experiments actually measured, and what the results mean for the future of physics requires first understanding CPT symmetry in detail. What does it actually demand of the physical world? What specific, testable predictions does it make? Why do physicists believe in it so deeply? And what would happen, theoretically and practically, if it turned out to be wrong? The answers begin with the three individual symmetries and how each one cracked, one by one, under the pressure of experimental evidence. Because the story of CPT symmetry is also the story of broken expectations. The story of physicists who assumed the universe was elegant and symmetric, who assumed nature would not prefer one direction over another or one type of matter over another, and who discovered, repeatedly and shockingly, that they were wrong. Each broken symmetry was a crisis. Each crisis led to deeper understanding. And when all the pieces are assembled, what emerges is not chaos, but a constraint more rigid than anyone anticipated. A boundary that all the violence of the Big Bang and all the precision of CERN's instruments cannot breach. That boundary is the subject of what comes next. For most of the 20th century, physicists believed the universe was fundamentally ambidextrous. They believed that nature did not care about left or right, that if you built a perfect mirror and watched any physical process through its reflection, the reflected version would obey the same laws as the original, that if you swapped every particle of matter for its antimatter counterpart, the physics would remain unchanged. That if you filmed any interaction and played the footage backward, the reverse sequence would look equally valid. These were not wild guesses. They were assumptions so deeply embedded in the mathematical structure of physics that questioning them felt almost absurd. Symmetry was beauty. Beauty was truth. And truth, physicists assumed, meant the universe treated left and right, matter and antimatter, forward and backward, with perfect impartiality. They were wrong about all of it, and the way they discovered they were wrong is one of the greatest detective stories in the history of science. Start with parity, the letter P in CPT. Parity transformation takes every spatial coordinate and flips it through the origin. Left becomes right, up becomes down, forward becomes backward. It is the mathematical equivalent of viewing the world in a perfect mirror. For decades, every known force in physics respected this symmetry. Electromagnetism does not care whether a current flows through a wire shaped like a left hand or a right hand. Gravity pulls objects downward regardless of whether the experiment is set up on the left side of a room or the right. The strong nuclear force, which binds quarks together inside protons and neutrons, shows no preference for any spatial orientation. Parity seemed safe, untouchable, a fundamental feature of how the universe operated. Then in 1956, two theoretical physicists at Columbia University asked a dangerous question. Tsung-Dao Lee and Chen-Ning Yang noticed something peculiar about the weak nuclear force, the force responsible for radioactive beta decay, the process by which a neutron inside an atomic nucleus transforms into a proton while emitting an electron and an antineutrino. The weak force had strange properties that did not fit neatly into the same mathematical framework as the other forces. Lee and Yang examined the experimental evidence carefully and realized something startling. Nobody had ever actually tested whether the weak force respected parity. Physicists had simply assumed it did, because every other force did. Assumption is not evidence. Lee and Yang proposed specific experiments that could settle the question. The challenge was taken up by Chien-Shiung Wu, an experimental physicist also at Columbia, in collaboration with scientists at the National Bureau of Standards. Wu designed an experiment of extraordinary elegance. She took cobalt-60 nuclei, which are radioactive and decay through the weak force, and cooled them to temperatures just above absolute zero. At such low temperatures, the thermal vibrations that normally randomize atomic orientations become negligible. She then applied a strong magnetic field to align the nuclear spins of the cobalt atoms, essentially pointing them all in the same direction. If parity symmetry held, the electrons emitted during beta decay should fly off equally in all directions relative to the nuclear spin axis. The mirror image of the experiment should look identical to the original. There should be no preferred emission direction. Wu found the opposite. The electrons were emitted preferentially in one direction, opposite to the nuclear spin. The distribution was dramatically asymmetric. In the mirror, the nuclear spin would flip direction, but the electron emission pattern would not compensate correctly. The mirror version of the experiment would give a different result than the original. The weak nuclear force violated parity symmetry. The universe was not ambidextrous after all. It had a built-in preference. Nature could tell left from right. The result hit the physics community like an earthquake. Wolfgang Pauli, one of the greatest theoretical physicists of the 20th century, had previously declared that he could not believe God was a weak left-hander. After Wu's experiment, Pauli reportedly said he was glad he had not bet anything. Lee and Yang received the Nobel Prize in Physics in 1957, the same year the experimental result was published. Wu, despite designing and executing the experiment that confirmed their prediction, was not included in the prize. Her exclusion remains one of the most debated omissions in Nobel history. The fall of parity shook the foundations of physics, but physicists regrouped quickly. They proposed a rescue. Perhaps parity alone was not the right symmetry to demand of nature. Perhaps the true symmetry was the combination of parity and charge conjugation, the operation that swaps every particle for its antiparticle. This combined operation, called CP, would mean that if you simultaneously reflected everything in a mirror and swapped matter for antimatter, the resulting process would be identical to the original. Parity violation alone was not a disaster. It simply meant that the weak force distinguished left-handed particles from right-handed particles. CP symmetry would restore the balance by demanding that what the weak force did to a left-handed particle, it would do identically to a right-handed antiparticle. The universe would still be fair. The mirror was cracked, but replacing matter with antimatter in the reflection would fix it. This hope lasted exactly 7 years. In 1964, James Cronin and Val Fitch at Brookhaven National Laboratory conducted an experiment studying neutral kaons. Kaons are particles containing a strange quark paired with either an up or a down quark. Neutral kaons exhibit one of the most bizarre behaviors in particle physics. They oscillate. A neutral kaon can spontaneously transform into its own antiparticle and back again, flickering between matter and antimatter states billions of times per second. This oscillation creates two distinct physical states with different lifetimes. The long-lived neutral kaon typically decays into 3 pions. The short-lived neutral kaon decays into 2 pions. If CP symmetry held perfectly, the long-lived kaon would never decay into 2 pions. That channel would be forbidden by the symmetry. Cronin and Fitch set up their detector at the end of a long beam pipe, far enough from the kaon production point that all the short-lived kaons had already decayed. Only long-lived kaons should reach their detector, and the only decays they should observe were 3 pion decays. Instead, they found a small but unmistakable signal of 2 pion decays. Approximately 2 out of every 1,000 long-lived kaon decays produced 2 pions instead of 3. CP symmetry was violated. The combined operation of reflecting in a mirror and swapping matter for antimatter did not leave the physics unchanged. The universe distinguished not only between left and right, but between matter and antimatter in a way that even the mirror plus swap rescue could not fix. The discovery of CP violation earned Cronin and Fitch the Nobel Prize in Physics in 1980. But more importantly, it opened a window onto the matter-antimatter asymmetry of the universe. CP violation means that certain processes produce slightly more matter than antimatter or vice versa. It provides a mechanism, at least in principle, for the universe to develop the imbalance that allows everything to exist. But as physicists measured CP violation more precisely, a frustrating picture emerged. The effect was real, but nowhere near large enough. The imbalance it could generate fell catastrophically short of what the universe required. A problem already introduced, but one that deepened with every improvement in measurement. Whatever tipped the cosmic balance, it was not CP violation alone. Additional sources remain undiscovered. Now consider time reversal, the letter T. Time reversal symmetry means that the laws of physics should look the same whether time flows forward or backward. If you filmed a billiard ball collision and played it in reverse, Newton's laws would be equally satisfied. The reversed movie would look like a perfectly valid physical process. For most forces, time reversal symmetry holds precisely. Electromagnetism is time reversal symmetric. Gravity is time reversal symmetric. The strong nuclear force is time reversal symmetric to extraordinary precision. But the weak nuclear force, the same troublemaker that broke parity and CP, breaks time reversal symmetry as well. This was confirmed directly in 2012 by the Babar experiment at the Stanford Linear Accelerator Center, studying the oscillations and decays of neutral B mesons, particles containing a bottom quark. The Babar collaboration demonstrated that certain transitions between quantum states proceeded at measurably different rates depending on the direction of the transition. The rate of transforming from state A to state B was not identical to the rate of transforming from state B to state A when the appropriate time reversal operation was applied. The arrow of time has a meaning at the subatomic level. The weak force can tell past from future. So by the early 21st century, the scorecard was clear. Every individual symmetry in the CPT triad had been broken. Parity violated. Charge conjugation violated. Time reversal violated. The pairwise combinations were also broken. CP violated in Carn decays, B meson decays, and eventually D meson decays. And if CPT symmetry holds while CP is violated, then T must also be violated, which was confirmed independently. Every piece of the triptych, examined in isolation or in partial combination, showed cracks. And yet when all three transformations are applied simultaneously, the cracks disappear. This is the central mystery and the central marvel of CPT symmetry. The universe violates each individual component. It distinguishes left from right. It treats matter and antimatter differently. It differentiates the past from the future. But it does all of this in a precisely coordinated way such that the combined operation of all three transformations leaves the laws of physics perfectly unchanged. The violations cancel, the asymmetries balance. The broken pieces, when assembled together, form something whole. To appreciate why physicists find this so profound, consider what CPT symmetry actually demands of the physical world. The theorem makes predictions that are specific, quantitative, and testable to extraordinary precision. First, CPT symmetry requires that every particle and its antiparticle have exactly identical masses. Not approximately identical, not identical to within measurement uncertainty, exactly identical. The mass of a proton must equal the mass of an antiproton. The mass of an electron must equal the mass of a positron. The mass of a hydrogen atom must equal the mass of an antihydrogen atom. Any measured difference, no matter how small, would constitute a CPT violation. Second, CPT symmetry requires that every particle and its antiparticle have exactly identical lifetimes. If a free neutron decays with an average lifetime of approximately 14 minutes and 40 seconds, a free antineutron must decay with the same average lifetime. If a charged pion lives for 26 nanoseconds, a negative pion must live for exactly 26 nanoseconds. Any difference would signal a violation. Third, CPT symmetry requires that particles and their antiparticles have equal and opposite electric charges and equal and opposite magnetic moments. The absolute value of the proton's charge must equal the absolute value of the antiproton's charge. The magnitude of the electron's magnetic moment must equal the magnitude of the positron's magnetic moment. Any discrepancy would break the theorem. These predictions are remarkable because they are, in principle, infinitely precise. Most physical predictions come with built-in uncertainties. Quantum mechanics tells you the probability of a measurement outcome, not the exact result. Thermodynamics gives you average behavior, not individual molecular trajectories. But CPT symmetry predicts exact equalities. Zero difference, not small difference. Zero. This means that every improvement in experimental precision directly tightens the test. There is no flaw, no minimum measurable effect below which the prediction becomes untestable. You can always measure more precisely. And if you ever find a non-zero result at any precision, the symmetry is broken. This feature turns CPT into one of the most powerful tools in physics for probing the unknown. Because CPT is a theorem derived from the foundations of quantum field theory and special relativity, any violation would indicate that those foundations are incomplete or wrong. And those foundations encompass virtually everything physicists know about the subatomic world. Quantum field theory is the mathematical framework that combines quantum mechanics with special relativity. It describes particles as excitations of underlying fields that pervade all of space. The electromagnetic field gives rise to photons. The electron field gives rise to electrons and positrons. The quark fields give rise to quarks and antiquarks. Every known fundamental particle is associated with a corresponding quantum field, and the interactions between these fields are governed by mathematical rules called Lagrangians. The standard model of particle physics is the specific quantum field theory that describes the electromagnetic, weak, and strong nuclear forces and all the known fundamental particles. Lorentz invariance is the symmetry of special relativity. It states that the laws of physics are the same for all observers, regardless of their velocity or orientation, provided they are not accelerating. This symmetry is not just a theoretical preference. It is one of the most thoroughly tested principles in all of science. Every particle accelerator experiment, every cosmic ray observation, every measurement of the speed of light confirms Lorentz invariance to staggering precision. The Global Positioning System satellites orbiting Earth must account for relativistic effects to function correctly. If Lorentz invariance failed, GPS would drift by kilometers per day. The CPT theorem states that any quantum field theory respecting Lorentz invariance, locality, and vacuum stability must automatically be CPT symmetric. This is not a conjecture, it is a mathematical proof. Luders, Schwinger, and Pauli demonstrated this rigorously in the 1950s, and subsequent mathematical work has strengthened and generalized the result. The proof does not depend on the specific particles or forces in the theory. It does not depend on whether the theory is the standard model or some extension of it. It depends only on the structural properties of the framework itself. Any quantum field theory that satisfies the basic requirements will respect CPT automatically, necessarily, without exception. This is why a CPT violation would be so catastrophic for physics. It would not mean that some detail of the standard model needed adjusting. It would mean that the entire framework of quantum field theory, or special relativity, or both, contained a fundamental error. Every calculation performed using these frameworks over the past 8 decades would need to be reconsidered. Every experimental success they achieved would need to be reinterpreted. The most precisely confirmed predictions in the history of science would rest on flawed foundations. Some speculative theories actually predict tiny CPT violations and are therefore testable through precision measurements. These theories arise primarily in the context of quantum gravity, the still unfinished project to unify quantum mechanics with general relativity. General relativity describes gravity as the curvature of space-time. Quantum mechanics describes the behavior of matter and energy at the smallest scales. Both theories are spectacularly successful in their respective domains, but they are mathematically incompatible. They use different languages, different structures, different assumptions. Unifying them is widely regarded as the most important open problem in theoretical physics. Several approaches to quantum gravity suggest that at the very smallest distances, near the Planck length of approximately 1.6 times 10 to the minus 35 meters, the smooth, continuous spacetime described by Einstein breaks down. Spacetime might become discrete, quantized, grainy. It might develop a foam-like structure at the smallest scales, with tiny fluctuations in geometry occurring constantly. This granularity could create a preferred frame of reference, a background structure against which motion can be measured absolutely. Such a structure would violate Lorentz invariance. And through the CPT theorem, a violation of Lorentz invariance automatically implies a violation of CPT. Alan Kostelecki at Indiana University has developed a comprehensive theoretical framework called the Standard Model Extension that catalogues every possible way Lorentz invariance and CPT symmetry could be violated while remaining compatible with other established physics. This framework contains hundreds of parameters, each one describing a specific type and magnitude of possible violation. Each parameter can be constrained by a specific class of experiment. Measurements of particle masses constrain some parameters. Measurements of decay rates constrain others. Measurements of oscillation frequencies, magnetic moments, gravitational responses all feed into the framework, each one tightening the constraints on different corners of the parameter space. As of the most recent analysis, every single parameter in the Standard Model extension is consistent with 0. No CPT violation has been detected in any system at any energy scale through any experimental method. The constraints are extraordinarily tight. Some parameters are bounded at the level of parts in 10 to the minus 31. These are sensitivities so extreme that they probe energy scales approaching the Planck energy, far beyond what any particle accelerator can reach directly. CERN's experiments contribute some of the tightest constraints in the entire framework, particularly through measurements of antiproton and antihydrogen properties. This ability to probe physics at inaccessible energy scales is one of the most remarkable features of CPT tests. The LHC collides protons at energies of approximately 13 trillion electron volts. The Planck energy, where quantum gravity effects are expected to become dominant, is approximately 10 to the 19th giga-electron volts, a factor of 1,000,000 billion beyond the LHC's reach. No conceivable particle accelerator could reach the Planck energy directly. The energy required would demand an accelerator larger than the solar system. But precision measurements of CPT-sensitive quantities at low energies can constrain the effects of Planck-scale physics because even tiny violations at the highest energies would trickle down and produce measurable consequences at accessible scales. This trickle-down effect is why CPT experiments at CERN are not merely confirming the obvious. They are searching for whispers of quantum gravity, hints of new space-time structures, evidence that the smooth, continuous fabric of Einstein's relativity gives way to something different at the very smallest scales. Every measurement that finds CPT holding eliminates more theoretical possibilities. Every decimal place of precision gained closes another window through which Planck-scale effects might have manifested. There is another dimension to CPT symmetry that makes it uniquely important, and it connects directly to the matter-antimatter asymmetry problem. CPT guarantees that the total combined operation, swap charges, reflect space, reverse time, leaves physics unchanged. This means that at the deepest level, the laws of nature treat matter and antimatter with perfect equivalence under the combined transformation. A universe made of antimatter, reflected in a mirror, running backward in time, would be physically indistinguishable from our universe. The rules governing the antimatter mirror universe would be identical to the rules governing ours. This creates a sharp constraint on any attempt to explain the cosmic asymmetry. Whatever mechanism generated more matter than antimatter in the early universe must have done so without violating CPT. It must have exploited CP violation, which is permitted and observed, combined with out-of-equilibrium conditions, which cosmic expansion provides, and barrier number violation, which the standard model allows through exotic quantum tunneling processes. But all of these mechanisms must operate within the CPT boundary. They must produce asymmetry in the matter-antimatter balance while respecting the deeper symmetry that relates the two under the combined transformation. This constraint is both a limitation and a guide. It eliminates theories that try to explain the asymmetry by postulating fundamental differences between the properties of matter and antimatter. If someone proposes that antimatter is slightly heavier than matter, CPT rules this out. If someone proposes that antimatter decays slightly faster, CPT rules this out. If someone proposes that antimatter responds differently to gravity at the fundamental level, CPT makes a specific prediction that can be tested. Any proposed explanation must be consistent with matter and antimatter having exactly identical intrinsic properties, while the asymmetry arises entirely from dynamical processes in the early universe. This is a stringent requirement. It means the matter-antimatter asymmetry is not about what matter and antimatter are. They are identical in every measurable property, related by CPT. The asymmetry is about what happened to them, about the specific conditions and processes in the first moments of cosmic history that favored matter over antimatter. Understanding those processes requires new physics beyond the standard model, but that new physics is constrained by CPT to work within a specific theoretical corridor. The picture that emerges is one of extraordinary depth. Individual symmetries break. The universe has a handedness. It distinguishes matter from antimatter through CP violation. It distinguishes past from future through T violation. These broken symmetries create richness and complexity. They allow the weak force to drive nuclear processes that power stars. They allow CP violation to tip the cosmic balance toward matter. They allow the arrow of time to give the universe a direction, a narrative, a history. But beneath all this broken symmetry lies a deeper order, a combined transformation that the universe cannot violate, a rule that persists when every one of its components has been shattered. CPT symmetry is not a relic of a simpler time in physics. It is the mathematical backbone of the framework that explains everything physicists have ever measured at the subatomic level. It connects the structure of spacetime to the properties of particles. It links the arrow of time to the distinction between matter and antimatter. It is the thread that holds the fabric together even when individual strands have snapped. Testing this thread, pushing it to its breaking point with the most precise measurements ever performed, is what CERN's antimatter experiments were designed to do. The machines built for this purpose are nothing like the thundering violence of the Large Hadron Collider. They are quiet, delicate. They trap individual antiatoms in magnetic cages and cool them to temperatures colder than the cosmic void. They hold antiprotons in electromagnetic bottles and measure their heartbeat, the tiny quantum oscillations that reveal their mass and magnetic moment, with a patience and precision that borders on the meditative, so the theorem makes its demands. Equal masses, equal lifetimes, equal charges, equal magnetic moments. Exact equalities, not approximations, extending to every decimal place any instrument can reach. These are not suggestions. They are commandments written into the mathematical fabric of space-time and quantum mechanics. And they are commandments that can be checked. Because somewhere, in a quiet hall at CERN, physicists have spent decades building machines designed to do exactly that. Machines that manufacture antimatter atom by atom. Machines that trap it in magnetic cages colder than the void between galaxies. Machines that measure its properties with a precision so extreme it probes physics at energy scales no accelerator will ever reach. They went looking for the crack that would bring the framework down. What they found instead was something nobody expected. The hall that houses CERN's antimatter experiments does not look like the kind of place where the foundations of reality get stress tested. There are no towering detector systems here. No caverns carved from solid rock. No 7,000-ton instruments wrapped in superconducting magnets. The antiproton decelerator hall is modest by CERN standards. A large rectangular building at ground level, industrial lighting overhead, concrete floors with painted safety markings, cables running along the walls in organized bundles. The machines inside are the size of large dining tables, not apartment buildings. They hum quietly rather than roar. Technicians move between them with the careful, unhurried demeanor of watchmakers, rather than the controlled urgency of collider operators. But what happens in this building is among the most extraordinary experimental work taking place anywhere on Earth. Scientists here routinely accomplish something that would have been considered outright impossible 40 years ago. They manufacture atoms made entirely of antimatter. They hold those atoms suspended in magnetic fields for hours. They shine lasers through them and measure which frequencies of light they absorb. They drop them and watch which direction they fall. And they compare every measurement, digit by digit, against the equivalent measurement for ordinary matter, looking for a discrepancy, looking for the moment the numbers diverge, looking for the crack in CPT symmetry that would signal the deepest revolution in physics since quantum mechanics itself. They have not found it, not because they have not looked hard enough, because it does not appear to exist. The journey from raw antiprotons to trapped antiatoms is a chain of escalating improbability. It begins violently. A beam of protons from CERN's proton synchrotron, accelerated to an energy of 26 billion electron volts, slams into a block of iridium metal. The impact is catastrophic at the subatomic level. Protons shatter against iridium nuclei, and the concentrated energy of each collision produces a spray of new particles. Among those particles, roughly one collision in a million generates an antiproton-proton pair. The antiprotons emerge, traveling at close to the speed of light, scattering in all directions, mixed with a blizzard of other particle debris. Collecting these antiprotons is the first miracle. Magnetic lenses gather the antiprotons into a rough beam and direct them into the antiproton decelerator ring. Here, over a period of about 1 minute, the antiprotons are slowed from 96% of the speed of light down to roughly 10%. The deceleration is achieved through a combination of magnetic manipulations and a technique called stochastic cooling, invented at CERN by Simon van der Meer, which squeezes the chaotic swarm of antiprotons into a tighter, more orderly beam. The cooled antiprotons are then passed to ALINA, the extra low-energy antiproton ring, which decelerates them further still, reducing their energy by another factor of 50. By the time antiprotons leave ALINA, they are travelling slowly enough to be captured in electromagnetic traps, but slowly enough is a relative term. These antiprotons still carry energies equivalent to temperatures of millions of degrees. Injecting them directly into a precision experiment would be like trying to study snowflake geometry using a flamethrower. Further cooling is essential. The experiments accomplish this through a technique called sympathetic cooling, where antiprotons are mixed with clouds of pre-cooled electrons in a penning trap. The electrons radiate away their kinetic energy through synchrotron radiation, losing heat rapidly. The antiprotons, sharing the same trap, collide gently with the electron cloud and gradually transfer their energy to the electrons, which radiate it away. Over minutes, the antiprotons cool to temperatures approaching the ambient temperature of the trap walls, just a few degrees above absolute zero. At this point, the antiprotons are cold and slow. They sit in electromagnetic cages, thousands of them, waiting. The next step depends on which experiment they are destined for, and each experiment asks a different question about the same underlying symmetry. The alpha experiment asks the most audacious question of all. It asks whether an atom made entirely of antimatter is identical to an atom made of matter. Not identical in some abstract mathematical sense. Identical in the way that matters most to physics. Identical in every measurable property. To answer this question, alpha must build antihydrogen. Ordinary hydrogen is the simplest atom in nature. One proton, one electron. The proton sits at the center, positively charged. The electron orbits around it, negatively charged. The electromagnetic attraction between them creates a bound state whose energy levels are among the most precisely known quantities in all of science. The 1s to 2s electronic transition in hydrogen, the energy difference between the ground state and the first excited state of the same orbital angular momentum, has been measured to approximately 15 digits of precision. It is one of the gold standards of modern physics. If there were a Nobel Prize for being measured well, hydrogen's 1s to 2s transition would have won it decades ago. Antihydrogen mirrors this structure exactly. One antiproton at the center, negatively charged. One positron orbiting around it, positively charged. CPT symmetry demands that every energy level, every transition frequency, every spectroscopic property of antihydrogen must match hydrogen perfectly. Not to a good approximation, perfectly. Any deviation, at any decimal place, would constitute a CPT violation. Building antihydrogen requires bringing antiprotons and positrons together under controlled conditions. The positrons come from a separate source. A radioactive sodium-22 isotope emits positrons through beta plus decay. These positrons are accumulated in a dedicated trap, cooled and compressed into a dense cloud containing millions of particles. The antiprotons, already cooled in their own trap, are then gently mixed with the positron cloud in a carefully tuned electromagnetic environment. When an antiproton passes close enough to a positron, electromagnetic attraction can capture them into a bound state. An antihydrogen atom forms. But this process is extraordinarily inefficient. The newly formed antiatoms emerge with a wide distribution of energies. Most are far too energetic to trap. They slam into the walls of the apparatus within microseconds of their creation and annihilate, producing a flash of pions and gamma rays that the detectors record as confirmation that antihydrogen was produced but immediately lost. To understand the difficulty of what comes next, you need to appreciate the scale of the trapping challenge. Antihydrogen is electrically neutral. Unlike the charged antiprotons and positrons from which it is assembled, it carries no net electric charge. You cannot hold it in place using electric fields. You cannot push it around with voltage differences. The only handle available to experimentalists is the tiny magnetic moment of the antihydrogen atom, a feeble response to external magnetic fields that is millions of times weaker than the electric forces used to trap charged particles. Alpha uses a magnetic minimum trap, a configuration of superconducting magnets that creates a three-dimensional magnetic well. Antiatoms in the right quantum state, the low field-seeking states, experience a force pushing them toward the center of the trap where the magnetic field is weakest. But the trapping force is absurdly feeble. The magnetic well is shallower than almost any other trap in physics. Only antihydrogen atoms with kinetic energies below about half a Kelvin, roughly 500 millikelvin in temperature terms, move slowly enough to be confined. Out of every 10,000 antihydrogen atoms produced in a mixing cycle, perhaps one or two are cold enough to be trapped. The rest annihilate on contact with the apparatus walls. Each annihilation is a tiny defeat. Each trapped atom is a tiny victory. Alpha detects the survivors by their absence, by the fact that no annihilation signal appears at the moment of creation, and then by deliberately releasing them later and observing the annihilation signal as confirmation that a trapped antiatom existed. The path from concept to success was neither short nor smooth. The idea of trapping antihydrogen had been discussed since the 1980s, but the technology did not exist to make it feasible. The Athena experiment at CERN produced the first cold antihydrogen atoms in 2002, creating tens of thousands of antiatoms in a controlled laboratory environment, but Athena could not trap them. The antiatoms were created and immediately lost, annihilating on the walls of the apparatus within microseconds. It was like watching a rare butterfly emerge from its cocoon and immediately fly into a fire. You knew the creature existed. You had proof it was real, but you could not hold it long enough to study it. The Alpha collaboration formed with the specific goal of solving this problem. Years of development followed. New trap geometries were designed. New magnet configurations were tested. Cooling techniques were refined. Positron accumulation methods were improved. The mixing process, in which antiprotons and positrons are brought together to form antiatoms, was optimized through hundreds of iterative experiments, each one adjusting voltages and timing and temperatures by tiny increments. The collaboration had to solve problems that had no precedent in experimental physics. How do you diagnose what is going wrong inside a trap when the thing you are trying to trap annihilates the moment it touches any surface? How do you know whether your trap is failing because the antiatoms are too hot, or because the magnetic well is too shallow, or because some stray electric field is pushing them off course? Each variable had to be isolated and tested independently, a process that consumed years. In 2010, the breakthrough came. The Alpha collaboration announced that they had trapped antihydrogen atoms for the first time. They held 38 antiatoms for approximately 170 milliseconds each. The achievement made headlines around the world. 38 atoms, held for less than a fifth of a second. It sounds modest, but those 38 atoms represented the first time in history that neutral antimatter had been confined in a laboratory. Every one of those antiatoms was an object that does not exist naturally anywhere on the surface of this planet, an atom whose components were manufactured in violent collisions, slowed to near absolute zero, assembled from their constituent parts, and then held in place by magnetic fields barely strong enough to support a cobweb. But 170 milliseconds was not long enough for precision measurements. The experiment needed to hold antiatoms for much longer. Over subsequent years, incremental improvements in trap depth, cooling techniques, and positron management extended the trapping time. By 2011, antiatoms were held for over 1,000 seconds, more than 16 minutes. Each extension required solving new problems. Longer trapping times demanded better vacuum conditions, because a single collision with a residual gas molecule would annihilate the trapped antiatom instantly. They demanded more stable magnetic fields, because fluctuations in field strength could eject the antiatom from its shallow well. They demanded better thermal isolation, because any heat leak into the trapping region would warm the antiatom beyond the trapping threshold. Recent experimental runs have held anti-hydrogen atoms for hours, long enough to perform spectroscopy, long enough to shine a laser through them and see what happens. The spectroscopic measurement that alpha has pursued most aggressively is the 1s to 2s transition. This is the same transition measured to 15-digit precision in hydrogen. Performing it on antihydrogen requires irradiating the trapped antiatoms with laser light at a very specific ultraviolet frequency, approximately 243 nanometers. If the laser frequency matches the transition energy of antihydrogen, the antiatoms absorb the photons and jump to an excited state. Excited antiatoms in certain quantum states are expelled from the magnetic trap because their magnetic moment flips sign in the excited state, reversing the trapping force. The expelled antiatoms annihilate on the walls, and the resulting pion signals are recorded. By scanning the laser frequency and observing where annihilation events spike, alpha maps the spectral line of antihydrogen. The result, published in 2018 in the journal Nature, found that the 1s to 2s transition frequency in antihydrogen agrees with hydrogen to a precision of 2 parts in 10 to the 12th power, 2 parts per trillion. To feel the weight of that number, consider an analogy. Imagine measuring the distance from the Earth to the Sun, a distance of approximately 150 million kilometers. 2 parts per trillion of that distance equals about 300 meters. Alpha is measuring the spectral frequency of an atom made of antimatter, an atom assembled from particles that were manufactured in collisions, decelerated across 9 orders of magnitude in energy, combined in magnetic traps at temperatures colder than outer space, and held in magnetic fields barely strong enough to suspend a dust grain, and finding that its properties match ordinary hydrogen to the equivalent of 300 meters out of 150 million kilometers, no difference detected. CPT symmetry holds. Alpha has also measured the hyperfine structure of antihydrogen. In hydrogen, the interaction between the magnetic moments of the proton and the electron splits the ground state into 2 closely spaced energy levels. The transition between these levels produces microwave radiation at a frequency of approximately 1420 MHz. This is the famous 21 centimeter line, one of the most important frequencies in radio astronomy, used to map neutral hydrogen gas across the Milky Way and throughout the cosmos. Alpha stimulated this same transition in antihydrogen and measured the corresponding frequency. The result agrees with hydrogen to a precision of a few parts in 10,000, less precise than the 1s to 2s measurement, but consistent. CPT holds again. Each spectroscopic measurement represents years of effort. Each decimal place of precision gained requires improvements in trap stability, laser control, positron accumulation, antiproton cooling, and data analysis. The Alpha collaboration includes more than 50 physicists from over a dozen institutions, all focused on measuring properties of a substance that does not naturally exist on Earth. They are building a body of evidence, measurement by measurement, spectral line by spectral line, that antihydrogen is indistinguishable from hydrogen. While Alpha builds antiatoms, the BASE experiment takes a different approach. BASE does not construct antihydrogen. It studies the antiproton itself, isolated and alone, trapped in a penning trap and measured with a precision that represents one of the supreme achievements of experimental physics. A penning trap confines a charged particle using a combination of a uniform magnetic field and a quadrupole electric field. The magnetic field forces the particle into a circular orbit. The electric field confines the particle along the axis of the magnetic field. Together, these fields create a 3-dimensional cage that can hold a single charged particle indefinitely. BASE traps individual antiprotons in this way and then measures 2 fundamental properties, the charge-to-mass ratio and the magnetic moment. The charge-to-mass ratio is the most direct test of whether antiprotons have the same mass as protons. CPT demands exact equality. BASE measures this ratio by observing the cyclotron frequency of a trapped antiproton, the frequency at which it orbits in the magnetic field. This frequency depends directly on the charge-to-mass ratio and the magnetic field strength. By comparing the cyclotron frequency of a trapped antiproton with that of a negatively charged hydrogen ion, which serves as a proxy for the proton, BASE extracts the ratio with extraordinary precision. The result is agreement to 69 parts per trillion. 69 parts per trillion means that if the antiproton were a banknote and you tried to detect whether it was counterfeit by weighing it, you would need a scale capable of detecting a difference equivalent to a single bacterium sitting on a stack of currency weighing several tons. That is the level of scrutiny BASE applies to every antiproton it measures. And at that level, the antiproton charge-to-mass ratio matches the proton value to 11 significant digits. No difference has been found. The magnetic moment measurement is even more challenging. The magnetic moment of a proton or antiproton is tiny, roughly 660 times smaller than that of an electron. Measuring it for a single trapped particle requires detecting individual quantum jumps between spin states. The antiproton in the trap can exist in one of two spin orientations relative to the external magnetic field: spin up or spin down. These states have slightly different energies due to the interaction between the particle's magnetic moment and the field. BASE detects which spin state the antiproton occupies by measuring a minute shift in one of the particle's oscillation frequencies. The shift is so small that detecting it requires the trap to be extraordinarily stable, with magnetic field fluctuations controlled to parts per billion and temperatures held below 1.5 Kelvin. The double penning trap technique, a key innovation by the BASE collaboration, separates the measurement into two steps performed in two different trap regions. In one region, called the analysis trap, the spin state is determined through the frequency shift method. In the other region, called the precision trap, a microwave drive attempts to flip the spin by applying radiation near the spin flip frequency. By repeatedly driving and measuring, BASE maps out the resonance curve and extracts the magnetic moment with a precision of approximately 1.5 parts per billion. The result matches the proton magnetic moment. To 9 significant figures, the antiproton and proton have the same magnetic moment, differing only in sign. CPT holds. BASE has also demonstrated something remarkable about antiproton longevity. In the course of their measurements, they have kept individual antiprotons trapped for more than a year. A single antiparticle, suspended in a magnetic bottle, surviving for over 12 months in a laboratory on a planet made entirely of matter. Every atom in the walls surrounding the trap, every molecule of residual gas in the vacuum chamber, every stray photon of thermal radiation represents a potential annihilation event. The vacuum inside the BASE trap must be maintained at pressures below 10 to the minus 18 millibar, among the lowest pressures ever achieved in a laboratory setting. At that pressure, the average time between collisions with a residual gas molecule exceeds the trapping duration. The antiproton sits alone in near-perfect emptiness, a single speck of antimatter surviving for months in a universe of matter. It is worth pausing to appreciate what these two experiments, alpha and BASE, are collectively accomplishing. They are attacking the same question from opposite ends of the complexity spectrum. BASE studies the antiproton in isolation, stripped of all context, a naked particle measured with the highest possible precision. Alpha studies the antiproton embedded within an atomic structure, bound to a positron, exhibiting the full richness of quantum mechanical energy levels. If CPT symmetry held for the bare antiproton but failed for the antihydrogen atom, it would mean that the binding interaction itself, the electromagnetic force holding the antiatom together, behaved differently for antimatter than for matter. If CPT held for the antiatom but failed for the bare antiproton, it would mean that the intrinsic properties of the antiproton were slightly wrong, but somehow conspired to produce the right answer when assembled into an atom. Both scenarios are physically implausible but experimentally distinguishable. The fact that both experiments confirm CPT independently, using different physical systems and different measurement techniques, provides a far more stringent constraint than either could alone. While alpha and base measure the static properties of antimatter particles and antiatoms, the LHCb experiment probes CPT from an entirely different direction. LHCb does not trap antimatter. It watches antimatter being created and destroyed in the violence of proton-proton collisions at the Large Hadron Collider. Its focus is on particles containing heavy quarks, particularly bottom quarks and charm quarks, which exhibit rich and complex decay patterns governed by the interplay of all the fundamental forces. Neutral B mesons are particles composed of a bottom antiquark paired with a down quark, or vice versa. Like neutral kaons before them, neutral B mesons exhibit the quantum mechanical phenomenon of oscillation. A neutral B meson can spontaneously transform into its own antiparticle and back again, flickering between matter and antimatter states approximately 500 billion times per second. The oscillation frequency depends on the mass difference between the two quantum mechanical eigenstates of the system. CPT symmetry demands that the mass and decay width of the B meson equal those of the anti-B meson. Any difference would manifest as a specific pattern in the oscillation behavior that LHCb's detectors could identify. LHCb has measured the CPT violating mass difference between the B meson and anti-B meson with a precision of approximately 10 to the minus 14 gigaelectron volts. The result is consistent with zero. No CPT violation has been detected. LHCb has performed similar measurements in the charm meson system, where D mesons oscillate between matter and antimatter states, and in the strange meson system, where the original CP violation was discovered. In every case, the CPT violating parameters are consistent with 0 to the limits of experimental precision. These measurements add a crucial third dimension to the CPT picture. Alpha works at energies measured in millielectron volts, the tiny energy scales of atomic transitions. Base works at energies of a few electron volts, the energy scales of trapped particle oscillations. LHCb works at energies measured in billions of electron volts, the violent aftermath of proton collisions at nearly the speed of light. CPT symmetry must hold across this entire range. The fact that all three experimental programs find no violation provides a constraint that spans more than 15 orders of magnitude in energy. It means CPT is not just an approximate low-energy symmetry that breaks down at high energies. It is not a high-energy symmetry that fails when particles slow down. It holds everywhere. At every energy scale physicists have been able to probe, in every system, through every experimental approach. The most dramatic test of CPT symmetry at CERN's antimatter facility came in 2023, and it answered a question that had been debated by physicists for decades. Does antimatter fall up or down? The question sounds almost silly. Of course antimatter falls down. Gravity attracts mass, and antimatter has mass. But the question is deeper than it first appears. General relativity describes gravity not as a force between masses, but as the curvature of space-time caused by energy and momentum. The equivalence principle, one of the cornerstones of Einstein's theory, states that gravitational and inertial mass are identical. This principle has been tested to extraordinary precision for ordinary matter, but it had never been tested directly for antimatter, not once. In the entire history of physics, no one had ever dropped an antiatom and watched which way it went. Some speculative theories proposed that antimatter might experience repulsive gravity, that antiatoms would fall upward in Earth's gravitational field. If true, this would have profound implications for cosmology and for our understanding of the fundamental forces. It could potentially explain the apparent absence of large-scale antimatter structures in the observable universe. It might even provide a mechanism for the accelerating expansion of the cosmos, replacing or supplementing dark energy. But antimatter anti-gravity would also create severe theoretical problems. CPT symmetry, combined with the equivalence principle and the general framework of quantum field theory, strongly predicts that antimatter must respond to gravity in the same way as matter. Anti-gravity for antimatter would imply a violation of one or more of these foundational principles. The alpha-G experiment was built to settle the question. It is a variant of the standard alpha apparatus, redesigned with a vertical orientation so that trapped antihydrogen atoms can be released and their trajectories observed as they fall under gravity. The experimental concept is elegant. Trap antihydrogen atoms in a magnetic well, gradually reduce the strength of the trapping fields. As the fields weaken, the antiatoms escape. If gravity pulls them downward, more antiatoms should escape through the bottom of the trap than the top. If antigravity pushes them upward, the pattern reverses. The engineering challenges were formidable. Antihydrogen atoms in the alpha-G trap have kinetic energies corresponding to temperatures of roughly 500 millikelvin. At that temperature, the average speed of an antihydrogen atom is roughly a few meters per second. The gravitational potential energy difference across the roughly 20 centimeter height of the trap is comparable to this kinetic energy, which means the gravitational signal is just barely detectable above the thermal motion of the antiatoms. It is like trying to hear a whisper at a rock concert. The signal is there, but the noise threatens to drown it completely. Extracting a clear directional signal required hundreds of experimental cycles and careful statistical analysis. The result was published in the journal Nature in September 2023. Antihydrogen falls downward. The measured gravitational acceleration is consistent with the standard value of g, approximately 9.8 meters per second squared, within the experimental uncertainty of about 25%. Antimatter is attracted to Earth, not repelled. The equivalence principle holds for antiatoms. CPT survives. The current precision of the AlphaG measurement is not yet sufficient to provide a high-precision test of the weak equivalence principle for antimatter. A 25% uncertainty means the gravitational acceleration of antihydrogen could differ from that of hydrogen by up to a factor of roughly 1.2 without being detected. Future upgrades aim to reduce this uncertainty to the 1% level, which would provide a meaningful test of whether antimatter falls at exactly the same rate as matter. The G-bar experiment, another antimatter gravity project at CERN, aims for even higher precision using a different technique. G-bar plans to create ultra-cold antihydrogen ions, strip the extra positron at a precise moment, and measure the resulting freefall trajectory with interferometric precision. If this program succeeds, it will push the gravitational test of CPT symmetry to a level where even tiny deviations from equivalence could be detected. Together, these four experimental programs paint a remarkably consistent picture. Alpha measures the internal energy structure of antihydrogen and finds it identical to hydrogen, to parts per trillion. Base measures the intrinsic properties of the antiproton and finds them identical to the proton, to parts per billion and parts per trillion respectively. LHCb measures the oscillation and decay behavior of mesons and antimesons at high energy and finds no CPT violating asymmetry at any measurable level. Alpha-Ga drops antimatter and confirms that it falls downward like ordinary matter. 4 experiments, 4 different physical systems, 4 different energy regimes spanning 15 orders of magnitude, 4 different measurement techniques developed independently by different teams with different expertise. One result: CPT symmetry holds. The engineering behind these measurements operates at the absolute frontier of what is physically possible. Superconducting magnets maintain fields stable to parts per billion over hours and days. Cryogenic systems hold temperatures below 1 Kelvin for months at a stretch. Ultra-high vacuum systems achieve pressures lower than the space between galaxies. Laser systems produce light with frequencies controlled to parts in 10 to the 15th power. Data acquisition systems register individual quantum jumps of single trapped particles, recording events that last billionths of a second and involve energy changes smaller than the thermal fluctuations of a single molecule. Each improvement in any of these technologies tightens the CPT constraint. Each experimental run pushes the boundary further, And each result returns the same answer. Zero deviation, no crack. No hint of a violation in any system at any scale through any method. The absence of a CPT violation is not a disappointment. It is not a failure to discover something. In precision physics, a confirmed symmetry is itself a discovery. Every measurement that finds CPT holding eliminates theoretical possibilities that were genuinely open before the measurement was performed. Every tightened constraint closes doors through which new physics might have entered. Every null result reshapes the landscape of what is theoretically possible, pushing speculative models into narrower and narrower corners of parameter space. Before these measurements were made, it was genuinely possible that antihydrogen had a slightly different spectrum than hydrogen. It was possible that antiprotons were slightly heavier or lighter than protons. It was possible that antimatter fell upward. These were not fringe ideas. They were open scientific questions with theoretical motivations from quantum gravity, from alternative cosmological models, from extensions of the Standard Model. The CERN experiments did not confirm what everyone already knew. They answered questions that needed answering, and the answers, in every case, pointed in the same direction. The rule holds, the constraint is real, the boundary does not yield. The evidence is on the table. 4 experiments, 15 orders of magnitude in energy, decades of refinement, trillions of annihilation events recorded, measurements pushed to parts per trillion and beyond. And across all of it, across every system and every technique and every energy scale, the same silence. No violation, no anomaly, no crack, just a symmetry holding firm against the most sustained experimental assault ever directed at a single physical law. But silence in physics is never empty. When the most precise instruments ever built return a null result at this level of sensitivity, the absence itself reshapes the landscape. Entire families of theories collapse. Boundaries tighten around what the universe permits. And the question shifts. It is no longer whether CPT symmetry holds. It is what it means that nothing can break it. There is a peculiar kind of victory that looks like failure. When experimentalists at CERN set out to test CPT symmetry, they were hunting for a crack in the deepest foundation of modern physics. They spent decades designing machines. They invented new trapping technologies. They cooled antimatter to temperatures colder than anything that exists naturally in the universe. They developed measurement techniques sensitive to differences smaller than 1 part in a trillion. They pushed the precision of human observation to limits that would have been considered physically impossible a generation earlier. And after all of that, after thousands of person-years of effort and hundreds of millions of euros of investment and engineering challenges that tested the absolute boundaries of what materials science and cryogenics and vacuum technology can achieve, they found nothing. Zero deviation, zero anomaly, zero hint of a violation. In almost any other field of human endeavour, spending decades searching for something and not finding it would be considered a defeat. In precision physics, it is among the most powerful results imaginable, because the nothing that CERN found is not empty, it is dense with meaning. The nothing that CERN found is not empty, it is dense with meaning. What looks like an absence of discovery is actually the most comprehensive map ever drawn of where new physics cannot hide. Decades of measurement have swept through the theoretical landscape like a searchlight, and what that light reveals is a terrain far more constrained than most physicists expected when the program began. Consider the landscape of theoretical physics beyond the Standard Model. Hundreds of proposals exist for how to extend or replace the current framework. Some invoke extra dimensions of space, curled up too small to observe directly but influencing particle properties in subtle ways. Some propose that space-time is not continuous but discrete at the smallest scales, built from fundamental units like atoms of space that create a preferred frame of reference. Some suggest that the constants of nature are not truly constant, but vary slowly across cosmic time, or from one region of the universe to another. Some introduce entirely new forces, new particles, new symmetry structures that connect matter and antimatter in ways the standard model does not. Many of these proposals, perhaps most of them, predict violations of CPT symmetry, not because their authors intended to violate CPT, often quite the opposite, but the mathematical structure of the CPT theorem is so tightly woven into the foundations of quantum field theory and special relativity that departing from either framework almost inevitably produces CPT violating consequences. Introduce a discrete space-time structure, and Lorentz invariant suffers, which means CPT suffers. Introduce a preferred cosmic frame of reference, and the same chain of consequences follows. Propose that fundamental constants vary with time, and the delicate balance that maintains CPT can be disrupted. Each of these theoretical directions makes specific, calculable predictions for how CPT violation would appear in experimental data. The predictions have specific magnitudes, specific signatures, specific dependencies on the type of particle, the energy scale, the measurement technique. The standard model extension developed by Alan Kostelecki catalogues these predictions systematically. It contains hundreds of parameters, each one representing a different possible way CPT and Lorentz symmetry could be violated. Each parameter can be constrained by specific experiments. Some are bounded by measurements of photon propagation from distant astrophysical sources. Some are bounded by atomic clock comparisons. Some are bounded by neutrino oscillation data. And some, among the tightest constraints in the entire framework, come directly from CERN's antimatter experiments. When BASE measures the antiproton charge-to-mass ratio to 69 parts per trillion and finds it identical to the proton, it does not just confirm a single prediction. It simultaneously constrains dozens of parameters in the standard model extension. When alpha measures the 1s to 2s transition in antihydrogen to 2 parts per trillion and finds it identical to hydrogen, it constrains a different but overlapping set of parameters. When LHCb finds no CPT violating asymmetry in B meson oscillations, yet another set of constraints tightens. The experiments attack the parameter space from different directions, using different physical systems at different energy scales. The result is a comprehensive assault on the possibility of CPT violation that leaves almost nowhere for new physics to hide within the currently accessible range. Some of the constraints reach sensitivities that probe physics at energy scales far beyond what any particle accelerator can achieve directly. The Planck energy, approximately 10 to the 19th gigaelectron volts, is the scale where quantum gravitational effects are expected to become dominant. The LHC operates at energies roughly 1,000,000 billion times lower than this. No foreseeable accelerator technology could bridge that gap, but precision measurements of CPT-sensitive quantities at low energies can detect the faint downstream consequences of Planck scale effects. Even a tiny modification to the structure of spacetime at the smallest distances would produce measurable ripples in the properties of particles at accessible energies. The absence of such ripples in CERN's measurements places bounds on Planck scale physics that are, in some cases, more stringent than any other experimental constraint available. This reach is what gives CPT tests their unique power. They are not limited to probing physics at the energy of the experiment itself. They leverage the mathematical structure of the CPT theorem to amplify their sensitivity, turning low-energy precision into high-energy discovery potential. It is as if measuring the surface of a pond with sufficient accuracy could tell you about earthquakes occurring thousands of kilometers below the ocean floor. The connection is not obvious, but it is mathematically rigorous, and the CERN measurements exploit it to the fullest. But the elimination of theoretical possibilities is only half the story. The other half concerns what CPT symmetry, confirmed to such extraordinary precision, tells us about the matter-antimatter asymmetry of the universe. This is where the results become not just informative, but genuinely constraining on the direction of future research. The universe is made overwhelmingly of matter. This is an observational fact confirmed by every measurement available. The cosmic ratio of matter to antimatter is approximately 10 billion to 1. Something in the first moments after the Big Bang generated this imbalance. The Sakharov conditions, formulated in 1967, identify three necessary ingredients for generating a matter-antimatter asymmetry from an initially symmetric state. There must be processes that violate baryon number conservation. There must be CP violation, and there must be departure from thermal equilibrium. The Standard Model satisfies all three conditions, but not by enough. Baryon number violation occurs through quantum tunneling processes called sphalerons, which are exponentially suppressed at energies below the electroweak scale, but were active in the hot early universe. CP violation exists in the quark sector through the complex phase in the CKM mixing matrix, the same CP violation measured at CERN and elsewhere. And departure from thermal equilibrium could have been provided by the electroweak phase transition, the moment when the Higgs field acquired its non-zero value and gave mass to the W and Z bosons. The problem is quantitative. The CP violation in the Standard Model is too small by roughly 9 orders of magnitude to explain the observed asymmetry. The electroweak phase transition, calculated within the Standard Model, turns out to be a smooth crossover rather than the sharp first-order transition needed to drive matter away from thermal equilibrium strongly enough. The sphaleron processes were active, but without sufficient CP violation and sufficient departure from equilibrium, they could not generate the observed imbalance. The Standard Model gets the qualitative picture right. Matter-antimatter asymmetry can develop through these mechanisms, but the quantitative prediction falls catastrophically short of observation. New physics is needed, additional sources of CP violation, a modified electroweak phase transition, perhaps entirely new baryogenesis mechanisms, operating at energy scales far above the electroweak scale. This is where CPT symmetry becomes a guide rather than merely a constraint. Whatever new physics generates, the cosmic asymmetry must respect CPT. This is not a minor technical requirement. It is a fundamental boundary that shapes the entire landscape of viable theories. CPT symmetry guarantees that the intrinsic properties of matter and antimatter are identical. Their masses are equal, their lifetimes are equal, their charges and magnetic moments are equal and opposite. The asymmetry, therefore, cannot arise from any inherent difference between matter and antimatter. It must arise entirely from dynamical processes, from what happened to matter and antimatter in the specific conditions of the early universe, not from what matter and antimatter fundamentally are. This eliminates a large class of otherwise plausible explanations. Any theory that tries to explain the cosmic asymmetry by postulating that antiprotons are slightly heavier than protons is ruled out. Any theory proposing that antineutrons decay slightly faster than neutrons is ruled out. Any theory suggesting that antimatter couples to the Higgs field differently than matter is constrained by CPT to produce identical rest masses. These are not strawman proposals. They represent genuine theoretical directions that were considered seriously before precision measurements closed them off. The surviving theories must work within the CPT boundary. Leptogenesis, one of the leading candidates, proposes that the asymmetry originated in the lepton sector rather than the quark sector. Heavy right-handed neutrinos, particles not included in the Standard Model but predicted by many extensions of it, could have been produced in the early universe and decayed asymmetrically, creating more leptons than antileptons. This lepton asymmetry would then be partially converted into a baryon asymmetry through sphaleron processes. The mechanism respects CPT because the CP violation driving the asymmetric decay arises from complex phases in the neutrino mass matrix, not from any intrinsic difference between neutrinos and antineutrinos. Electroweak baryogenesis remains viable if the electroweak phase transition was more strongly first order than the Standard Model predicts. Extensions of the Higgs sector, such as adding a second Higgs doublet or a singlet scalar field, can modify the phase transition dynamics while remaining fully compatible with CPT symmetry. These scenarios predict additional scalar particles that might be discovered at the LHC or at future colliders. Other mechanisms operate at even higher energy scales. Grand unified theories, which attempt to merge the electromagnetic, weak, and strong forces into a single framework, predict baryon number violation. through the decay of super-heavy gauge bosons with masses around 10 to the 16th giga-electron volts. These decays could generate the cosmic asymmetry directly, and they respect CPT because the underlying grand unified theory is itself a quantum field theory, satisfying the theorem's requirements. CPT does not tell physicists which of these mechanisms is correct, but it tells them where to look and where not to look. It narrows the search space. It provides a boundary condition that any successful theory of baryogenesis must satisfy. And every improvement in the precision of CPT measurements tightens that boundary further, eliminating more exotic possibilities and focusing theoretical attention on the most promising directions. What remains genuinely unknown, even after decades of CPT tests, is substantial. 3 questions stand out as defining the frontier. First, does CPT symmetry hold at energy scales far beyond current experimental reach? The most precise tests probe physics up to, and in some cases beyond, the Planck scale, but they do so indirectly, through the downstream effects of high-energy violations on low-energy observables. It remains possible that CPT holds perfectly at accessible energies, but breaks at scales where quantum gravitational effects dominate, and the smooth structure of space-time gives way to something fundamentally different. Testing this directly would require experiments at energy scales that are physically inaccessible with any foreseeable technology. But indirect probes continue to improve, and each improvement narrows the window for high-energy violations. Second, does CPT symmetry hold in strongly curved spacetime? The CPT theorem is proven within the framework of quantum field theory and flat Minkowski spacetime, the spacetime of special relativity. General relativity tells us that spacetime is curved by mass and energy, and that this curvature is what we experience as gravity. The interaction between quantum mechanics and strongly curved spacetime is not fully understood. Near black hole singularities, in the first instance after the Big Bang, at the centers of neutron stars, spacetime curvature reaches values where the flat spacetime approximation breaks down. Whether CPT symmetry survives in these extreme gravitational environments is an open question that may require a complete theory of quantum gravity to answer. The alpha-gig measurement of antimatter's gravitational response provides a first step, but the precision needed to test CPT in the gravitational sector at a meaningful level is still orders of magnitude beyond current capability. Third, what is the precise mechanism that generated the matter-antimatter asymmetry? CPT constrains the answer, but does not provide it. Identifying the specific particles, forces, and processes responsible for the cosmic imbalance remains one of the central unsolved problems in physics. Progress on this front will likely require both new experimental discoveries, perhaps at the LHC, perhaps at future colliders, perhaps in neutrino experiments or gravitational wave observatories, and new theoretical insights that connect the known ingredients of baryogenesis to a complete quantitative account of the observed asymmetry. CERN is preparing the tools to address these questions. The high-luminosity upgrade of the Large Hadron Collider, scheduled to begin operations around 2030, will increase the collision rate by approximately a factor of 10. This flood of additional data will allow LHCb to make even more precise measurements of CP violation and CPT-sensitive observables in heavy quark systems. It will give ATLAS and CMS greater sensitivity to rare processes that could reveal new sources of CP violation or new particles contributing to the matter-antimatter asymmetry. The Antimatter program at the Antiproton Decelerator continues to advance. ALPHA is working toward higher precision spectroscopy of antihydrogen, aiming to match or approach the 15-digit precision achieved for hydrogen. BASE is developing new techniques to measure the antiproton magnetic moment with even greater accuracy. AlphaG and GBAR are refining their gravitational measurements, pushing toward the 1% level where meaningful tests of the weak equivalence principle for antimatter become possible. And on the horizon sits the most ambitious project in CERN's future, the feasibility study for the Future Circular Collider, a proposed accelerator with a circumference of approximately 91 kilometers, roughly 3.5 times the circumference of the LHC. The first phase of this machine would collide electrons and positrons at energies optimized for precision studies of the Higgs boson. The second phase would collide protons at energies up to 100 trillion electron volts, approximately 8 times the energy of the current LHC. These collisions would probe physics at scales never before accessed, potentially revealing new particles, new forces, and new sources of CP violation that could explain the cosmic asymmetry. The future circular collider is not approved. It faces significant technical challenges, enormous costs, and political hurdles. Much of the technology needed to build it does not yet exist. The superconducting magnets required to bend particle beams around the ring at the proposed energies have not been developed. The project timeline stretches to the end of the 21st century, but if it is built, it will push the boundaries of fundamental physics into territory where CPT symmetry can be tested at precisions currently unimaginable, and where the mechanisms behind the matter-antimatter asymmetry might finally be revealed. There is something worth pausing over in all of this, something that extends beyond the technical details of magnetic traps and oscillation frequencies and spectral lines measured to 12 decimal places. It concerns the kind of universe these measurements reveal us to be living in. Humans have spent centuries discovering that the universe is less orderly than it appears. Classical mechanics gave way to the probabilistic uncertainty of quantum theory. The stable, eternal cosmos of ancient philosophy gave way to an expanding universe born in a hot, dense singularity. The elegant symmetries that physicists expected to find at the subatomic level, parity, charge conjugation, CP, each shattered in turn when experiments probed deeply enough. The history of physics is, in many ways, a history of broken expectations, a history of the universe refusing to be as simple, as symmetric, as beautiful as theorists hoped. CPT symmetry reverses this narrative. Here, for once, the universe is more orderly than anyone had a right to expect. Individual symmetries break. The weak force violates parity. Nature distinguishes matter from antimatter through CP violation. The arrow of time has meaning at the subatomic level. Each of these violations was a surprise. Each one forced physicists to abandon cherished assumptions. Each one revealed a universe more complex, more nuanced, more asymmetric than the elegant equations suggested. But beneath all that broken symmetry, at the very bottom of the mathematical structure, sits a rule that does not break. A combined transformation that absorbs every individual violation and emerges unchanged. The universe allows nature to distinguish left from right. It allows nature to treat matter and antimatter differently. It allows nature to differentiate past from future. But it demands that when all three distinctions are applied simultaneously, the total picture remains perfectly symmetric. The violations are permitted, but they are coordinated. They cancel, they balance. The deepest level of reality maintains a coherence that survives the shattering of every symmetry above it. This is not the kind of discovery that makes headlines about physics being broken or reality being an illusion. It is quieter than that, more subtle, but in many ways more profound, because it tells us that the universe is not chaotic. It is not arbitrary. It is not a collection of unrelated facts and forces thrown together without structure. There is an architecture to reality, a set of constraints so deep that no physical process, no matter how extreme, appears able to violate them. The Big Bang did not violate them. The most energetic collisions ever produced on Earth do not violate them. The most precise measurements ever performed cannot detect even a whisper of deviation. The rigidity of CPT symmetry carries a message about the nature of physical law itself. Laws of physics are not just descriptions of how things happen to behave. They are boundaries on what is possible. The speed of light is not merely the speed at which electromagnetic radiation happens to travel. It is a structural limit embedded in the geometry of space-time, a boundary that no amount of energy or ingenuity can overcome. The uncertainty principle is not merely an inconvenience in measurement. It is a fundamental constraint on what can be simultaneously known about a quantum system. These are not suggestions, they are walls. CPT symmetry belongs in this category. It is not an observed regularity that might someday be overturned by better data. It is a mathematical consequence of the most thoroughly tested principles in physics, quantum mechanics and special relativity. To violate CPT would require abandoning one or both of these pillars, and those pillars have been tested, confirmed, and relied upon across every domain of physics for the better part of a century. They underpin every electronic device, every medical imaging system, every satellite navigation network, every nuclear reactor on Earth. They are not approximations awaiting correction. They are, as far as any measurement can determine, exact descriptions of how the universe operates at its most fundamental level. The physicists at CERN, who test CPT symmetry, are therefore not merely checking a theoretical prediction. They are probing the structural integrity of reality. They are asking whether the universe is as deeply ordered as the mathematics suggests. And the answer, returned with a precision that spans 12 decimal places and covers energy scales from milli-electron volts to beyond the Planck scale, is yes. This result does not close the book on fundamental physics. It opens it to a specific chapter. The chapter where the mystery of the matter-antimatter asymmetry must be solved within the constraints that CPT imposes, where new physics must respect the boundary even as it introduces new particles, new forces, new sources of CP violation, where the search for quantum gravity must account for a symmetry so rigid that it has survived every test thrown at it for 7 decades. The unknown remains vast, but it is shaped, bounded, constrained by a rule that the universe itself appears unable to break. There is an old idea in physics, going back to Einstein, that the universe is comprehensible, that the laws governing its behavior can be understood by the minds it produces, that the same cosmos which builds stars and planets and thinking beings also builds the mathematical structures those beings need to understand it. CPT symmetry is evidence for that idea, not proof, evidence. A sign that the architecture of reality is not just complex but elegant, not just functional but structured, not just vast but coherent. Deep beneath the farmland of the French-Swiss border, in a hall where the machines hum quietly and the technicians move with the patience of watchmakers, the most precise measurements in the history of science continue. Each run of each experiment adds another digit of confirmation. Each improvement in trap stability or laser precision or vacuum quality pushes the boundary further, and each result returns the same answer. The rule holds. The universe breaks parity. It breaks charge conjugation. It breaks CP. It breaks time reversal. It allows asymmetry and complexity and the arrow of time and the distinction between matter and antimatter. But it draws a line, a final boundary, a constraint so deep it appears woven into the mathematical fabric of existence itself. And nothing humanity has ever built, not the most powerful accelerator, not the most precise measurement, not the most violent collision, has found a way to cross it. CPT symmetry is not a cage, it is a skeleton, the structure that holds everything else together. And the extraordinary discovery of CERN's antimatter program is not that physics is broken. It is that physics is, at its deepest accessible level, more rigid, more consistent, more precisely ordered than anyone had reason to expect. The hidden rule holds. Reality cannot break it. And that, in the end, may be the most astonishing thing about the universe we inhabit.